Welcome back. This is BMA1102, Calculus 1. We had started earlier and we stopped at derivatives of functions, and we started with derivatives of implicit functions. So today we continue from where we stopped, and we are getting the derivative of the exponential function. And the exponential function is the function f of x is equals to a raised to power x, where a is the constant. So a is greater than 0, of course, and then x is the exponent and a is a constant. So a is greater than 0, like we've said there. We have the natural exponential function, which is expressed as e to the x. So the natural exponential function is expressed as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x raised to power 4 over 4 factorial plus, where of course 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, and 4 factorial of course is 4 times 3 times 2 times 1. So if we are looking for the derivative of this function, that would imply that we are getting of e to the x, and the derivative of 1 will be 0. The derivative of x is going to be 1. This will give us 2x over 2 factorial, plus this will give us 3x squared over 3 factorial plus 4x squared over 4 factorial, and this is continuous. So which implies that the derivative of this natural exponential function will give us (1) plus x plus, because the 2 will cancel, plus x squared over 2 factorial plus x cubed this is cubed, sorry, that should be cubed because we are finding the derivative of this. It should give us cubed there. So that is plus x cubed over 3 factorial, and that is continuous. So what you realize is that the derivative of the exponential function is basically the same, or is exactly the same as the exponential function. So the derivative of the exponential function is just the exponential function itself. Now generally the rule for differentiating where functions where the exponent is compounded is, so we can say that the rule here is you take the original function, you multiply by the derivative of the exponent. So our original function times the derivative of the exponent of the given function. So for example, if you're supposed to get the derivative of e raised to power, let's say 3x, this implies that the derivative is going to be, this is our original function or our original exponent, and then our original exponential, and then we multiply by the derivative of the exponent. Our exponent here is 3x. So the derivative of 3x is 3. So this will give us 3e 3x. We can do a second example to this. You have y as raised to power a half x plus 2. So we are saying that the derivative is going to be, we take the original function as it is, so that would give us 2e a half x plus 2, and then we multiply by the derivative of the exponent. Our exponent here is a half x plus 2, so that would give us times a half. So this implies then that our derivative is e raised e to the a half x plus 2. Then maybe we can introduce a product. So we have x squared e negative 2x as our next example. So this one is a product. So that implies that the product rule has to be taken into consideration. So, and remember the product rule, we say that if you are having a multiple of, or you have a product of two functions u and v, the rule is u bar v plus v bar u. So our u here is going to be x squared, and our v is going to be e to the negative 2x. So u bar is going to give us 2x, and v bar will give us negative 2e 2x. Then we can now find what our dy over dx is. So this will give us u bar v, so that would be 2x e negative 2x, and then plus v bar u, we have a negative, so that is negative 2 e negative 2x x squared. So we can express that as 2x e negative 2x minus 2x squared e to the negative 2x. So we can choose to factor out what is common in the two. So you can choose to factor out 2x ex, so that would give us over, that would give us minus, so we'll have 2x as 2x e to the negative 2x into 1. So that would be 1 minus x is our answer. Then we can do one last example that would consider a function that is a quotient. So here we use the quotient rule. Quotient rule is u bar minus v by u over v squared. So our u here is this, our v is that, so u bar will be, and v bar will be 2x. Then the derivative is going to be, so this would be x squared, so that is u bar v, and then minus v by u, so that would give us 2x e to the x over v squared. So v is x squared, so that would give us x raised to power 4. So again here we can choose to factor out what is common. This would give us ex x minus 2 over x cubed, which would also give us x raised to power negative 3 x minus 2 ex. So all those are possible answers to that. So from the natural exponential function, we go to the derivative of the exponential function to base a. So exponential function to base a. So this is what we started with. At the beginning we said that it is a raised, or a to the power x, and by definition a to the x is expressed as e ln a of x. So then that implies that we can choose to differentiate this so that we can find a common way of finding the derivatives of a function if it's exponential function to base a, or we can use this to be getting the derivative for each using the same steps. So either way, the solution would still be the same. So let's see if we differentiate this with respect to x. This would give us the rule. So that would be, we are also differentiating this side. And we say that the derivative of the exponential function to base e is you take the original function, which is e ln a x, and then we multiply by the derivative of the exponent. So that would give us ln a. But then remember that this was actually our a to the x. This can also be expressed as ln a to the x. So with that, we can go to examples. So we have examples. And the first example we will do is y 3 raised to power x. So we have said that this will give us ln a. So we've said that it's ln a. So ln a, that would give us ln 3. And then as our solution or derivative, the second one is y is 5 raised to power x minus 2. So we use the same again. So this will give us ln 5, and then 5 we can introduce a product. So we have f of x or f of t. Let's change the variable. F of t is t squared 2t to t squared 2 raised to power t. We can write that again on this side where we have plenty of space. So we are saying f of t is t squared and then 2. So this is a product, t squared and 2 to the t, or 2 raised to power t. So we have to work it out that way. So if we use u, that would be that, and then v would be 2 to the t, so, or 2 raised to power t. So u bar would give us 2t, and then v bar would give us ln 2 2t. And then of course now we just need to get the derivative. So that would give us u bar v. So that would give us 2t, and then plus t squared ln 2 2t. Then we can still do another example where we have now a product. We have rather an exponent, a quotient 3 2t over t. So this is 3 to the 2t, or 3 raised to power 2t over t. So same thing again, we get what is our u. So our u in this case will be 3 raised to power 2t, and then our v will be t. So u bar v bar will be 1, and then u bar will still use the same ln 3, 3 to the 2t. Then after that we get, or let me put it as this, assuming that our function was y is a function of t. We can write it like that. So this would be u bar, so that would be ln 3, 3 to t, and then minus 3 over t squared. So we can choose to factor out 3 to the 2t, or we can just leave it as that. I will move to the next thing. So that would be derivative of the logarithm function. Derivative of the logarithm function. So we have different bases of the logarithm function, but we'll categorize them into two. We have the natural logarithm function, which is log to base e of x, generally just expressed as ln of x. So when we are getting the derivative of ln x, this is 1 over x. So we can prove this. We let y to be ln x, and then we differentiate both sides. So differentiate with respect to x. So that is y is ln x, and we are differentiating with respect to x. So that would give us dy over dx is equals to I think there's a step I've skipped there. So we are saying y is ln x, which implies that y is log to base e of x. So then from here we can be able to express this as e to the y is actually equal to x. Then from here we differentiate with respect to x on both sides. This will give us, remember that the derivative of the exponent is the original function times the derivative of the exponent. Our exponent here is y, but we need to remember that we're differentiating with respect to x. So that would give us dy over dx, and then this side will have 1. So that implies that our dy over dx is actually 1 over, but we have said that e to the y is equal to x. So that implies that our dy over dx is actually 1 over x. So a general rule here, where we have our functions that are compounded or composite, is you take derivative of the exponent, derivative of the inner function, derivative of inner function over the inner function. So if we let this inner function to be u, it implies that you're talking about u bar over u, where u is the inner function. So we can go to examples. So the first one is y is ln 7x. So our inner function here is 7x, so that will be our u, which implies that u bar is going to be 7. So our derivative is going to be u bar, which is 7, over the inner function, which is 7x. So that would give us 1 over x. Second example to this, we have y as ln of 8x squared minus 1. So our inner function here is 8x squared minus 1, and u bar will give us 16x over that inner function, which is 8x squared minus 1. If we bring in product, so this is the third example, we bring in the aspect of product here, ln x. So we have a product of two functions, x cubed and ln x. So we use the product rule. That would give us u as x cubed, u bar as 3x squared, and v as ln x, and v bar as 1 over x. So in that case, our derivative is going to be 3x squared ln x plus x squared. Then if we bring in an example that is quotient, same story again. So u bar here will be 1 over x. V bar is going to be a half x raised to power negative a half. So this is v bar. V is x raised to power half. V bar will be a half x raised to power negative a half. So we get the derivative. It will be u bar v. So u bar will be, and our v is ln x, and v is root of x, or x raised to power a half. So that is u bar v, and then minus v bar u. So v bar u will be a half x raised to power negative a half ln x. Our u is ln x, our v is that, over v squared. So v squared will be root of x squared. So this will give us, this is x raised to power a half. So that will give us x raised to power negative 3 over 2. Minus. So what I didn't write here was u, which is our ln x, and our v, which is x raised to power half. Just to go through the steps again. So u bar is going to be the derivative of that, which will give us 1 over x, and then v bar will be the derivative of this, which will give us a half x raised to power negative a half. Then du over dx will be u bar v. So we have u bar v, that would be 1 over x times x raised to power a half, minus v bar u. V bar u would be a half x squared, a half x raised to power negative a half times ln x. So this would be 1 over x, and then you're multiplying by that x raised to power a half. So this is the same as x raised to power negative 1, and then we have times x raised to power a half. So that will give us negative a half. So that should be negative a half. And then minus a half x raised to power negative a half ln x over. So this would give us x. This is a half, and then squared. That would give us that. Okay. So we can move to the next logarithm functions to base a. So log functions to base a. So where we have log to base a of x. I remember when you're starting on the log functions, I said that we'll categorize them into two. We have to base e and all the other bases. So a here comprises of all those other bases. Common log, that is to base 10, and all the rest. So log to base a of x can be expressed in terms of log to base e. So this would give us log to base e of x over log to base e of a. So once we have it that way, we can write this now as ln x over ln a. Then if we want to get the derivative of this, log to base a of x, I would find the derivative of ln x over ln a. So again, that's a quotient. We have u, we'd have u as ln x, and you'd have v as ln a. So u bar would be 1 over x, and then v bar would be 0, because ln a is just a constant. So then that implies that our derivative would be u bar v, so that would be ln a 1 over x plus 0 over minus 0. That's minus 0 because it's quotient. It's the quotient rule. So that is minus, and then over v squared. V is ln a, and it is squared. So that implies that this will give us 1 over x ln x ln a, which we can write as 1 over ln a x. Okay. So then that implies that if we are looking for the derivative it is 1 over ln a x. We can go to examples. So the first example, so these are examples, and the first example we have is y is log to base 3 of x. So following that rule, dy over dx will give us 1 over ln 3 x. If you have b as log to base 10, y is log to base 10 of 7x, then the derivative is going to be a same thing again, 1 over ln 10 x. last example on this, we have y is log to base 5 of x squared minus 1 root of that. So this is a function within a function. So we have x squared minus 1 raised to power a half. So u bar will give us, that would be 2x times a half, x squared minus 1 raised to power negative a half. So this will give us x into x squared minus 1 raised to power negative a half. So that implies that y is log to base 5 of u, because that is what we are expressing as our u. So dy over dx over du here, we are differentiating y with respect to u, that is, will give us 1 over ln 5 of u. So this will give us our dy over dx, as we get the product of the two, and of course we substitute what u is, so that would give us 1 over ln 5, and then we have u is x squared minus 1 raised to power a half, and then we are multiplying that by the derivative of our first function that was within that function, so times x squared minus 1. There's an x here which we should not forget, so there's that x. So by virtue of this, we can sort that out. So that would give us our dy over dx as 1 over ln 5, and then that would be x squared minus 1, and then what will remain up here will be x. So our answer is basically x over ln 5 x squared minus 1. Okay, so next we move to derivatives of trigonometric functions. So derivatives of trigonometric functions. Derivatives of trigonometric functions. So of sine x is cos x, the derivative of cos x is negative sine x, the derivative of tan x is sec squared x, the derivative of sec x is sec x tan x, and then the derivative of cosec x is negative cosec x cot x, and then the last one the derivative of cot x is negative cosec squared x. Okay, so this same these derivatives can still be expressed in terms of for example, where we are saying the derivative of sine x is cos x, this can still be, because this might appear to be specific or subjective. So if we are talking about introducing a variable u, which is a differentiable function of x, then we can talk about it being sine u being equal to cos u bar, and then for cos u being negative sine u u bar. So those are both ways through which we can, what is important is to know how to use them. So we can prove a few of them. So we can prove that the derivative of sine x is cos x. So we use first principles, and f of x is going to be sine x. F of x plus change in x is going to be sine x plus change in x. Then we know that rule. So dy over dx will be limit as change in x tends towards 0, sine of x plus change in x minus sine of x over change in x. So from compound angles, that will give us a limit as change in x tends towards 0. This will be sine x cos change in x plus sine change in x cos x, and then minus sine x over change in x. So that would give us a limit as change in x tends towards 0 as sine x into cos change in x minus 1 over change in x, and then that would be plus cos x sine change in x over change in x. So we get the limit both sides. So this will give us sine x multiplied by 0. This would give us 0 plus cos x, and then the limit of this will give us 1. So that is cos x. So the derivative of sine x is cos x. To differentiate the cos, again you'd use the same first principles turn. You'd use quotient rule and so on. Sec, you use the fact that sec is 1 over cos, and then use the quotient rule. So let's go to examples. The first example that we have, the first example that we have is y is sine 4x minus 7. So this is a function within a function, and we treat it as such. So I will have u as 4x minus 7. So u bar will give us a 4. Then or du over dx will give us 4, and then that implies y is sine of u. So dy over du will give us cos u. So then we find the derivative. That would be the product of the two. So that would give us 4 cos u is 4x minus 7. Second example, we have y is 4 tan x squared plus 1. So like I said earlier, you have the option of using it in terms of sin x or tan x, or tan u. So if in case you want to use that, so this would just be the derivative being sec squared u bar. So in that case, that would be faster. So that would give us 4. 4 is a constant that is multiplying our function. And then u bar would give us 2x. And then we know this would give us sec squared of x squared plus 1. So this would give us 8x sec squared of x squared plus 1. And then we can do another example. We have a function here that is 1 plus sine t, and it's raised to power 4. So this is a function within a function. So we'll have u as 1 plus sine t. So this will give us u bar or du over dt is cos t. Then we can call our function maybe y. So that would give us u raised to power 4. So dy over du would give us 4 u raised to power 3. So dy over dt would give us so this would give us cos t, and then you multiply by, or u is 1 plus sine t, and it is cubed. So this would give us our answer as 4 cos t into 1 plus sine t cubed. Okay. One last example, we have f of x is 2ex cos x. So this is a product of two functions. We have the first function is 2e to the x, and then the second function is cos x. So we use product rule here, so this would be that, v would be cos x. So u bar would be 2ex, it remains as it is, and then v bar would be negative sine x, and then f bar of x would be u bar v, so that would give us 2ex cos x, and then plus, so that would give us a minus because of this, 2e to the x sine x. So we can write that as cos x minus sine x. So next we move to derivatives of inverse trigonometric functions. Derivatives of inverse trigonometric functions. Derivative of inverse trigonometric functions. Derivatives of inverse trigonometric functions. So inverse trigonometric functions can be expressed as either to the power -1 or arc. So those two terms can be used. So we have arc sine u. So this is the same as sine inverse of u. So the two are simply imply the same. So this one is u bar over square root of 1 minus u squared Of course, we are talking about u being a differentiable function of x, or u is differentiable at x. D over dx like cos u is negative u bar over root of 1 minus u squared cot u. This should be arctan. This is arctan. Let me write it up here. So that is arctan u. This would be u bar over 1 plus u squared. And then we can write the next one down here. So that is arc cot u. This will be negative u bar over 1 plus u squared. And then the derivative of arc sec u is u bar over the absolute value of u times u squared minus 1. And then the last one, arc cosec u is going to be a negative u bar over u squared minus 1. Okay, we can prove one of them. So proof, we proved that the derivative of arc sine x is 1 over root of 1 minus x squared. So if we let y to be sine inverse of x, this implies that it will be that if and only if sine y is equals to x. And this is for the values of pi. It should be y less than pi over 2. Yeah, values of y. So if that is the case, we can differentiate both sides with respect to x. So with respect to x, this will give us cos y, but we are differentiating with respect to x, and that would give us 1. So that implies that dy over dx is 1 over cos y. But we know that cos y is going to be 1 over square root of 1 minus sine squared y. And then we know that sine y is x, so that would give us 1 over square root of 1 minus x squared. Then we move to the last example on this. F of x is equals to arc cos x over x plus 1. So as much as this function has an inverse trigonometric function, majorly or mainly it is a quotient, so we have to use the quotient rule. So in using the quotient rule, our u is the arc cos x, and then our v is x plus 1. So our u bar is going to be negative 1 over root of 1 minus x squared, and then our v bar is going to be 1. So after that, Once we have our u bar and our v bar, we can go ahead and find our derivative. So this is f bar of x. We can title it either way. So this will give us negative x plus 1 over root of 1 minus x squared, and then minus arc cos of x. So that is u bar v, of course knowing that it's negative u bar, and then minus v by u. So v by u is what is giving us negative arc cos x minus that, and then we know that we are dividing all of this by v squared. So that's the same as multiplying by 1 over x plus 1 squared. My space is small there, so we can finish this up here or down here. So that would give us our derivative as negative 1. This is so this is u bar v, and then minus v by u. Okay, so this will give us negative 1 over x plus 1 root of 1 minus x squared minus arc cos x over x plus 1 squared. So we move to the next thing, that is derivatives of hyperbolic functions. Derivatives of hyperbolic functions. Hyperbolic functions are basically just special exponential functions, and they are defined as follows. So cos hyperbolic x is plus over 2, sine hyperbolic x is, and then tan hyperbolic x. So all the rest are described as, or are defined, or they are expressed in terms of these two. So tan we know is sine hyperbolic over cos hyperbolic. So that would give us over plus, so that is tan hyperbolic x. Then sec hyperbolic x, sec is 1 over cos, so that would give us 2 over plus, and then we have cosec hyperbolic x. This is 1 over sine, so this will give us 2 over minus, and then we have cot hyperbolic x, so this will be cos over sine, so that would give us over okay. So we can prove one of them. We'll prove the derivatives. So let's go to the derivatives first. So we have sine hyperbolic u. So u being a differentiable function of x, so this will give us cos hyperbolic u, rather u bar, and then the derivative of cos hyperbolic u will give us sine hyperbolic u, u bar. The derivative of tan hyperbolic u will give us sec hyperbolic squared u bar, and then the derivative of sec hyperbolic u will give us sec hyperbolic u tan hyperbolic u bar, and then cosec hyperbolic u, the derivative of this will give us negative just coming back to this, this should be negative. So sec hyperbolic u is negative, sec hyperbolic u bar, then cosec hyperbolic u is negative, cosec hyperbolic u cot hyperbolic u bar, and then the last one, that should be cot hyperbolic u is negative cosec hyperbolic squared u bar. Okay, so from here we can prove one. We can prove that the derivative of cos hyperbolic x is sine hyperbolic x. So what we are getting the derivative of is this function, and that's a quotient, so we need to have u and v, then get u bar and v bar. So u is this, which implies that our u bar is going to be minus, so that is our u bar, and then v is 2, v bar is 0. So then our derivative is going to be u bar v, so that would give us 2, so that is u bar v, sorry, and then minus v bar u, so v bar u is going to be 0, so that's minus 0, over v squared, v is 2, so that would give us 4. So this will give us which is sine hyperbolic x. So that clearly shows that cos hyperbolic x is sine hyperbolic x. We can move to examples. So examples, and the first example that we have or we'll do is we are given our function f of x as cos hyperbolic 3x minus 2. So we know that should give us sine hyperbolic u bar. So u is 3x minus 2, u bar will give us 3. So that implies that our derivative is going to be 3 sine hyperbolic u. And then the second example we have f of x as being equal to sec hyperbolic e to the 2x. So our u here is the exponential function e to the 2x. So u bar, so u is this, u bar is going to be 2e to the 2x. So then our derivative, we know that the derivative of sec hyperbolic, u is sec hyperbolic u, tan hyperbolic u, and then u bar. So this will give us our u bar is 2, and then sec hyperbolic, that is our u, tan hyperbolic. Okay, but it is negative. Remember, the derivative is negative. And then we move to the next example. This is our third example. f of x is cosec hyperbolic x. So it's an exponential function, and the derivative of an exponential function is the original function, or the original exponential, times the derivative of the exponent. So that would give us our original exponential function times the derivative of the exponent. Our exponent there is cosec hyperbolic x. So the derivative of cosec hyperbolic x is negative cosec. So that's negative, you can put it here. Cosec hyperbolic x cot hyperbolic x. Then the last example we can do is f of x, or the last example we'll do is this ln of sine hyperbolic x. So our u here is sine hyperbolic x, and remember the derivative of a log function is u bar over u, where u is the inner function. So our inner function is sine hyperbolic x, so u bar is going to be cos hyperbolic x. So then this is going to be a u bar, which is cos hyperbolic x, over our u, which is sine hyperbolic x. This is actually cot hyperbolic x. So then we move to derivatives of inverse hyperbolic functions. Derivatives of inverse hyperbolic functions. So our sine hyperbolic is square root of u squared plus 1. The derivative of cos hyperbolic inverse is u bar over square root of u squared minus 1. Then the derivative of tan hyperbolic inverse of u is going to be u bar over 1 minus u squared. That will be the same as the derivative of the cot hyperbolic inverse. Cot hyperbolic inverse of u is going to be the same, so that would give us u bar over 1 minus u squared, then of sec hyperbolic inverse of u. This will give us a negative u bar over u times the square root of 1 minus u squared. And then lastly, cosec hyperbolic inverse of u will give us over absolute value of u times square root of 1 plus u squared. So these inverse hyperbolic functions can be expressed also in terms of the natural exponential function. Remember that the natural exponential function and the natural log functions are actually inverses of each other. So like sine hyperbolic inverse of x can also be expressed as ln of x plus square root of x squared plus 1. So basically, if you take like a sine hyperbolic inverse of x, and you know that sine hyperbolic inverse is ex minus e negative x, and this ln. So if you find f of g of x, where g of x is the first function and f of x is the second function, then you'll find that each one of them, f of g of x will give you x, and g of f of x will also give you x. So by virtue of that, applying that the two are inverses. So they can be expressed in either of the two forms. So it's good to familiarize oneself with each of the two. So I go next to examples. Next we move to examples. And the first example that we have is y is cos hyperbolic inverse of 3x. So u is 3x, u bar here will give us 3. So after that, we just follow what we have already expressed as how the derivative takes this form. And then the second example, we have y is sec hyperbolic inverse of 1 over x. So our u here is 1 over x. So u bar is going to be negative x raised to power negative 2. So then, having that which is necessary, our dy over dx is going to be negative x raised to power negative 2. Negative, negative, so that would give us a plus over x raised to power negative 1, 1 minus x squared. So then this will give us 1 over x square root of 1 minus, this should be, this was, because our u, we said was x raised to power negative 1. So u squared will be x raised to power negative 2. So that should be raised to power negative 2, which is 1 minus 1 over x squared. So if you work out this, you will have, this will be over x squared. So this will be x squared minus 1. And then square root of x squared will be x, which will cancel with this. So that will leave us with 1 over root of x squared minus 1, which you can write as x squared minus 1 raised to power negative a half. Yeah. And then we go to one last example here. We're supposed to get third example, y is tan hyperbolic inverse of sine 2x. So our u here is sine of 2x. Our u bar is going to be 2 cos of 2x. So then the derivative, that would give us a u bar, which is 2 cos 2x over, this should be 1 minus, so 1 minus u squared. So u is sine 2x, so u squared will be sine squared 2x. So this is 2 cos 2x. 1 minus sine squared 2x is the same as cos squared 2x. So this is cos squared 2x. So this will give us, our answer is 2 over cos 2x. Okay. So next we move to parametric equations. Parametric equations. So parametric equations, so where we are talking about a smooth curve, probably we can title it C. And expressions for this smooth curve is x is equals to f of t and y is g of t. Basically the aspect of time getting into our concept here. So dy over dx is going to be dy over dt over dx over dx over dt. So for example, if you're given, so examples, let me do them on the next page. So examples, the first example you're given, x is t squared and y is 2t. Then dx over dt is going to be 2t. dy over dt will give us 2. So we are saying dy over dx is dy over dt, which is 2, over dx over dt, which is 2t. So this gives us 1 over t. Second example to this, we have x. So this is second example. We have x as sine squared theta, and we have y as cos squared theta. So here our parameter is theta, not t, but implication the same. So that would be 2 sine theta cos theta, and then dy over d theta will give us 2 cos theta sine theta. So that's a function within a function. So then we know that dy over dx will give us dy over dx will give us dy over d theta divided by, so that would give us 2. This one should be negative because the derivative of cos is negative sine. So this should give us 2 negative 2 cos theta sine theta over 2 cos theta sine theta, which will give us negative 1. That should give us negative 1. So just one last example. Example 3, we have x as e to the 2t and y as e the 3t, or e raised to power 3t. So dx over dt will give us 2e to t. dy over dt will give us 3e 3t. So dy over dx will give us 3e 3t over 2e 2t. So this will give us 3 over 2 e 3t e 2t. So this will give us 3 over 2 e t. This is negative. Yeah, so that is e to the t. Okay. So next we move to the last thing that we will be doing today, and that is higher order derivatives. So higher order derivatives, we look at higher order derivatives for algebraic functions, and then we move to also for implicit functions and parametric functions. So higher order derivatives. So we know that when you're given a function, the first derivative is the derivative of that function. If you're talking about the second derivative is the derivative of the first. And then the third is the derivative of the second derivative, and so on and so forth. So from this second derivative, that's what we refer to as higher order derivative. So it would be prudent to start from the notations. So we know that for first derivative, we say that the notations we use are f bar of x, y bar, dy over dx. We have d over dx of f of x, and then we have of y or f of x. So if you're talking about second derivative, second, that would be f double bar of x y double bar dx squared f of x so that continues up to the nth derivative, so that will be f y to the n and then this one would give us n of f of x, and then this last one would give us dx n of y. So like I have said, the second derivative is the derivative of the first derivative, the third of the second, and so forth. Let's go to examples. So the first example we have is we are supposed to get the third derivative. So that is y is 4x cubed minus 6x squared plus 5x minus 1. So this is the function you're given. We are supposed to get the third derivative. So first derivative will be our dy over dx, and that would be 12x squared minus 12x plus 5. Our second derivative will be 24x minus 12, and then our third derivative will be 24. So that gives us the solution to what has been asked of us. And then our second example to this, we have f of x is 3x raised to power 5 plus 2x raised to power 3 over 2 minus 1 over 4x. So our first derivative will give us 15x raised to power 4 plus 3x raised to power a half. Then this will give us plus 1 over 4 x raised to power negative 2. And then we get the second derivative of this. This will give us 16 x raised to power 3 plus 3 over 2 x raised to power a half minus a half x raised to power negative 3. So the question actually was we get the third derivative even here. So even here the question was we get the third derivative. So the third, so this will give us 180 x squared minus 3 over 4 x raised to power negative 3 over 2, and then this will be plus 3 over 2 x raised to power negative 4. So that would be the third derivative. So we do an example on exponential implicit functions rather. So we have x squared minus xy plus y squared is equals to 9, and we are supposed to get the second derivative. So this one we are getting the second derivative. So this will give us 2x minus, this is a product, so that will give us y plus x dy over dx, and then plus 2y dy over dx is equals to 0. So that implies that dy over dx is going to be y minus 2x over 2y minus x. Okay, so we want to get the second derivative. So this is a quotient. This is u and this is u bar. And at the same time, we remember that it's an implicit function. So we have to remember that we are differentiating with respect to. So we are differentiating with respect to x. So then u bar, this is u. So u bar will give us dy over dx minus 2. So that is u bar, and then v remains as it is, and then minus v bar. V bar will give us 2 dy over dx minus 1. So should have the bracket there. So v bar will give us 2 dy over dx minus 1. So that is v bar, and then we are multiplying it by u, and then over v squared. Our v is 2y minus x, and it is squared. So then if we open up that bracket, I will have 2y dy over dx minus x dy over dx minus 4y plus 2x minus 2y dy over dx plus 4x dy over dx plus y minus 2x, and it's all over 2y minus x squared. So this will give us there are those values that will disappear or will go, like this one and this one, and then we have this one and this one also. So this one will give us a 3x dy over dx. So that's 3x dy over dx. So this one has gone with this one, and then this one has gone with this one. So minus 3y over 2y minus x. This is 2y minus x squared. So then we factor in what dy over dx is. We insert the value of dy over dx. So we know that from our first step, our dy over dx was y minus 2x over 2y minus x. So we are subtracting 3y, and it is all over 2y minus x squared. So next, we open up this bracket and deal with the fraction. So this will give us 3xy minus 6x squared, and then this one will give us minus 6y squared plus 3xy over 2y minus x. This was squared together with this will give us cubed. And then we collect like terms. This will give us 6xy minus 6x squared minus 6y squared over 2y minus x cubed. Then we factor out what needs to be factored out. Of course, our interest is to see if we can be able to come with the original function, which is equated to 9, so that we can be able to replace that. So this will give us negative 6 into x squared minus xy plus y squared over this was 2y minus x cubed. Okay, but we know that x squared minus xy plus y squared is equals to 9, which is our original function. So that implies that negative 54 over 2y minus x cubed is the derivative of our function. Okay, so that is second derivative for an implicit function. We go to second derivative for parametric functions. So next is parametric functions. We do at least we can do one. So second order for parametric equations. So higher order for parametric. This is parametric equations or functions. So from remember that at the beginning we said that if you're given x as a function of t and y also as a function of t, the first derivative we said was dy over dt over, so this is first derivative over dx over dt. And we know that the second derivative is generally the derivative of the first. But for parametric equations, we divide by dx over dt. So that implies that we'll get, with respect to t, so this is dy over dx being equal to this. So we get the derivative of dy over dx with respect to t, and then we divide by dx over dt. So the process is the same up to the nth. So nth would be n minus 1 of our, so this would be, let me write it on this other side. So the nth derivative would be d over dt over dn minus 1 over dn minus 1 d, so dn minus 1 of x of, so that is dy over dx. So this would be dy dx n minus 1, and then we divide by dx over dt. So then if we go to examples, we are given x as t cubed plus t, and you are given y as t raised to power 5 plus 1. We are supposed to get the second derivative. So dx over dt will give us 3t squared plus 1. dy over dt will give us 5t raised to power 4. So the first derivative, which is dy over dx, will give us 5t raised to power 4 over 3t squared plus 1. Now the second derivative, we are saying we differentiate our first derivative and then we divide by dx over dt. So this one is a quotient, so we'll use quotient rule. So that would give us 20t cubed into 3t squared plus 1 minus 6t into 5t raised to power 4 over 3t squared plus 1 squared. So this is just the quotient rule, and then remember that you're supposed to divide this by dx over dt. So that's the same as multiplying by 1 over dx over dt, which is 3t squared plus 1. So this will give us 60 t raised to power 5 plus 20 t cubed minus 30 t raised to power 5 over 3t squared plus 1 cubed, which will give us our answer as 60 minus 30. That would give us 30 t raised to power 5 plus 20 t cubed over Let me write it on this other side so that it can be much more clearer. So this will give us 30 t raised to power 5 and then plus 20 t cubed over 3 t squared plus 1 cubed. So the last example, we have x is equals to 2 sine t and y is 3 cos t. So dx over dt, we are still getting the second derivative here. So dx over dt will give us 2 cos t and dy over dt will give us negative 3 sine t. So the first derivative, dy over dx, will give us negative 3 sine t over 2 cos t. Then we get the second derivative. So we get the derivative of our first derivative, which is a quotient. So using quotient rule, this will give us negative 6 sine squared t minus 6 cos squared t over 4 cos squared t. And then we are supposed to multiply by, we are dividing by 1 over 2 cos t. So this will give us our answer is negative 3 over 4 cos cubed t, which will give our answer as negative 3 over 4 sec cubed t. So we finish there for today. We still have applications of differentiation to go through, and that is where we will start in our next lesson. Thank you.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.